Another way by which I can improve the throughput is by a technique which basically observes that can I sort of break up the computation into multiple stages, right. So, let us go back to the basics of the FIR filter structure. Right. What was the problem that we had? This critical path equal to Tm plus 2 times Ta was 4 nanoseconds, okay. And the question that I am interested in asking at this point is there any way I can break that, I can reduce that critical path, okay. And the obvious way by which you can think of reducing the critical path is, after all, what is the definition of critical path? It is the delay from the output of some register until the input of some other register. So, if I could have introduced some other registers in the middle of this critical path, let us say for example that I could introduce a register out here, right. Now, I would have been able to break the critical path, okay, and I would have got this is a delay of Tm, this is a delay of 2 Ta, okay, max of Tm or 2 Ta. In this case both are the same, so it ends up being 2 nanoseconds. So yeah, actually yes, let me rephrase this, that is a good point. I will just erase this, I will just call this path delay on the whatever, on this highlighted path. The observation is correct. What he said was that there is actually another path which still has the B followed by 2 adders and so on. I am just talking about this highlighted path alone. For that I have managed to break it, okay. If I could similarly go around finding all the paths that have delay greater than 2 nanoseconds and break them into something where no path is a length greater than 2 nanoseconds, then potentially my critical path of my entire circuit would be 2 nanoseconds rather than the 4 that I originally had, okay. So, question is, how do I go about doing this? Am I allowed to just introduce registers anywhere as I like, okay? And the answer to that in general is no, you can't just introduce registers anywhere you like, because potentially it is changing the functionality of what you want to do, okay. One way of looking at it is to say, supposing I had this circuit, right, I have x of n, supposing this was all that there was to it, right. What is y of n in this case? What is the equation that is being implemented over here? It is basically taking b into x of n, right, this lower path, plus a into x of n minus 1, because there is a delay out there, okay. Now, what happens if I just arbitrarily introduce one register over here alone? This changes the equation to y of n equals b x of n minus 1 plus a x of n minus 1. This is a fundamentally different filter, right. I have changed the entire notion of what its transfer function looks like, so I cannot do this. But on the other hand, supposing I had something of this sort and I introduce one over here and one over here, right. Now, what happens? I have essentially got y of n equals b x of n minus 1 plus a x of n minus 2. The question is this the same as the original filter or not, or is there anything fundamentally different? Has anything fundamentally changed over here? Can I reasonably claim that this is pretty much the same as the original filter? Will it have the same transfer function? Will it have the same behavior, right? So, one way of looking at it to understand it a bit more clearly is to sort of say, can I write the corresponding transfer function, which basically looks something like this in terms of z transforms, b x of z plus a z inverse x of z, which means that y of z equals x of z into b plus a z inverse, right. Or alternatively, y of z by x of z, which is the transfer function, equals b plus a z inverse. In the second case, what I had was y of z equals b z inverse x of z plus a z inverse x of z, which basically gives us that y of z by x of z equals z inverse into b plus a. And in the third case, what I have is y of z equals b z inverse x of z plus a z to the minus 2 x of z, which gives us y of z by x of z equals z inverse into b plus a z inverse. Okay. Now you can sort of see a bit more clearly why the first one and the third one are the same, because just a multiplication by z inverse is essentially just delaying something in time. Okay. All samples are delayed uniformly in time by one sample period. Okay. They do not otherwise change the nature of the transfer function. In other words, if this was a low pass filter and basically had a cutoff at some particular frequency, the third function, the red transfer function over here, would also have a cutoff at exactly the same frequency, whereas the second one would essentially have been converted into an all pass, because there is no longer any dependency on z inverse as far as the function is concerned, right. It just takes the input data, multiplies by a constant b plus a and delays it by one time unit. Okay. So if there was some averaging or some particular cutoff frequency beyond which it should not be allowing frequencies, that has changed completely as far as the second, the orange one, is concerned. Whereas the first one and the third one have the same transfer function, the difference being that one of them has now got every output sample being delayed by one clock cycle, one sample period. Okay. So in that sense, we say that this original filter and the one where delays or the registers have been introduced on both the legs of this circuit are going to behave exactly the same, right. This step that we have applied over here is essentially something, the term that is used to refer to it is pipelining. Okay. The idea behind pipelining can be sort of illustrated a bit more easily in the context of just, take out the actual functionality, don't worry about multipliers, adders and so on, and now just look at a chain of different functions that are put together over here, right. Let us call them A, B, C and D, right. And in fact, if you look at the origins of the word pipelining, it is not from the domain of signal processing or even circuit design. It comes way before that. Sort of the first place where it was systematically put to use was in the automobile industry, right, by Henry Ford. Okay. The Ford approach to factory production essentially said that if I have to go through many steps in order to build a car, right, let us say that one of the steps is to basically take the chassis of the car, the second one is to fix the wheels onto it, the third one is to put the engine in place, the fourth one is to fix the doors, right. So let us say that I have, take the chassis, wheels, engine, doors. Okay. Obviously there are more steps involved in building a car, but maybe these are the main 4 steps that you have over here, right. The normal way by which cars would have been built was, I actually have this being done one after the other. Okay. Ford's innovation, so to say, was basically to say that, look, different people can be doing this at different times, right. So I have one part of the factory floor that I will just mark off as the chassis portion. Okay. Normally the way that it would work is the car would be in one particular place, people would come there, they would work on it, and once they are done, they would move away and the next group would come there and start fitting the wheels, the next group would come fix the engine, the next group would come fix the doors and then send the car out. Whereas what he said was, let's change this around, right? Keep the workers stationary, right, and let the job flow. Okay. Then there is another place where wheels are fitted, another place where the engine is fitted, and the final place where the doors are fitted, which means that the car itself basically would go through all of those stages one by one. Okay. So the way that it would work is, at time 0, so to say, the first car would appear over here, okay, and it would get the chassis put in place. After that it moves. So car 1 at time 1 would move on to the next place where it would be getting its wheels fitted. Okay. At that time, what would happen? Right. At the second time instant, t equal to 1, the chassis worker is now idle. Okay. Let him start working on the second car. Okay. At time 3 or t equal to 2, that car which was originally working on the chassis would now move to wheels. The one which has wheels already fitted would move to the engine, okay, and a new car can take its place as far as the chassis is concerned, right. And at t equal to 3, I would have the first one going through to get its doors fitted, the second one would be getting its wheels fitted or engine fitted, the third one would be getting wheels fitted, and the fourth one would just be starting. So this core idea that you keep the workers fixed and let the job flow through was originally applied in the context of the assembly line, so to say, right, that was used for assembling cars. The reason it's called a pipeline is because it sort of resembles the idea of water flowing through a pipe, right. The pipe itself remains stationary, the water or the job is the one that flows through it. Okay. Going back to a context of signal processing, right, the idea is once again the same. We have our hardware units that are just going to remain stationary and perform certain work, and the job or the sample that is being computed is going to flow through those hardware units.